So our next speaker is Anurag Sahay from Rochester, who will speak on moments of the Hurwitz zeta function with rational shifts. Please.
Okay. Thank you for the introduction and for letting me speak today. So for most of the talk, I'll be speaking about the moments of the Hurwitz zeta function with rational shifts. If I have time in the end, I'll speak a little bit about what happens when you have irrational shifts, and that part will be joint work with Winston Heap and Trevor Woolley. And actually, if you attended Trevor's talk on the first day of the conference, some of what I'll talk about is connected to that. Okay, so let me first introduce the overview of the talk. Is I'll first introduce what the Hurwitz zeta function is, because it's not something I expect everyone to be familiar with. Then I'll talk about moments generally, and then specifically moments of the Hurwitz zeta function. Okay, so the way the zeta function of Hurwitz is defined is very similar to the Riemann zeta function. But it's shifted by a shift alpha. So you take an alpha, which in the literature is usually restricted to being between 0 and 1, and you take the usual definition of the zeta function, which is 1 over n to the s, and you shift it by alpha. One thing I want to draw your attention to is that the way it's normalized in the literature is that you start the sum at n equals 0. So the zeta function actually corresponds to alpha equals 1, right? That's not a choice I would have made if I could rewrite the literature, but it is a choice. It is what's used in the literature, so that's how it's defined. There are a lot of similarities between the two zeta functions, so let me give you a list of them. One is the usual argument for showing that zeta is holomorphic in the half plane sigma greater than 1 goes through exactly to show that zeta s comma alpha is holomorphic in that region. Basically because it converges absolutely for sigma greater than 1 and uniformly if you're bounded away from 1. You can use several of the arguments that show how to take a metamorphic extension of zeta to the full plane to show that zeta s alpha also has a metamorphic extension. It also has a pole. The pole is at the same place at s equals 1, and the residue is the same. It's still 1. They both have trivial zero-free regions. By what I mean is the following. So if you think about where zeta is defined, this is the complex plane. This is sigma equals 1. In this part of the plane, you know that zeta doesn't vanish by the Euler product. That argument doesn't go through for the Hurwitz zeta function, but you can show there's another line a little further off over here, which is sigma equals 1 plus alpha. If you're at the right of this line, it doesn't vanish. This was shown by Spira in 1976, and just to compare, if you said alpha equals 1, it just says that the zeta function, the usual zeta function, doesn't vanish for sigma greater than or equal to 2. They both satisfy a functional equation. I have functional equation in quotes, which I'll explain in a bit. And those are similarities. So let me talk about the functional equation. So to talk about the functional equation, I'll have to introduce this new object. This is exactly the same as the zeta function, but it's exponentially twisted. So it's an additive twist in the numerator with the same parameter alpha. So the functional equation of the Hurwitz zeta functions is the following. Now, the one thing I want you to note is that this is not actually a functional equation. You're not relating zeta you're not relating the Hurwitz zeta function to itself. You're relating the Hurwitz zeta function to something else. But there is a sense in which this is a functional equation, which is that if you look instead at e to the 2 pi I n lambda over n plus alpha to the s, where you're looking at this. This quantity satisfies a similar relationship to this. And then this sum that I have over here is what you get when you put lambda equals alpha and alpha equals 0, alpha equals 1, while this quantity is what you get when you put lambda equals 1 and alpha equals alpha. I apologize for using alpha twice there, but hopefully it's clear what I mean. This is a special case of a more general functional equation for this thing, which is called the Lorentz zeta function. In any case, one thing I want to point out is that if you put alpha equals 1, this additive character just becomes the constant function 1. So this becomes zeta of s. And when alpha equals 1, this is already zeta of 1 minus s. So, if you plug zeta everywhere where you have p or zeta 1 minus s alpha, you reduce to what we usually call the functional equation of the Riemann zeta function. And perhaps one thing to point out is that these are both manifestations of the Poisson summation formula. Like if you know the usual proof of the functional equation for the Riemann zeta function, the same proof goes through, but instead of using 1 over n to the s, you use 1 over n plus alpha to the s. And on the Fourier side, that introduces this additive twist. Okay. But there are similarities, but there's also a lot of differences between the two types of functions. One is, so before I do that, let's quickly talk about this. When you put alpha equals 1, you get zeta s. If you put alpha equals 2, what you get is the following. It's n plus 1 over half to the s, n summed over 0. If you simplify this a bit, this is 2 to the s over 2n plus 1 to the s, sum from n greater than or equal to 0. And that's basically 2 to the s times the odd part of the zeta function, right? And so if you use the usual Euler product of zeta, that tells you that this quantity is exactly 2 to the s minus 1 times zeta s. So we have these two relationships between zeta s1 and zeta s alpha when alpha is 1.5. But other than these two values of the shift parameter, the Hurwitz zeta function isn't related to zeta in a direct way. And in particular, everything I say on this slide doesn't apply for alpha equals 1.5, but it does apply for any other choice. The Riemann zeta function has an Euler product. Other than alpha equals 1.5, the Hurwitz zeta function does not. Furthermore, zeta is zero free in the domain of convergence, right? So if I just to draw that picture again, here sigma equals 1, it's zeta is zero free to the right of this picture. But the Hurwitz zeta function is not. If you take what we know from Spira's result is that if you take this line, sigma equals 1 plus alpha, the Hurwitz zeta function is zero free on the right of here. But in between over here, actually, you can show that there are infinitely many zeros of the Hurwitz zeta function, which is quite different from how from what we know about the zeta function. This is not even in the critical strip. This was proved by Davenport and Heilbronn in 1936, and for rational and transcendental shifts, and Castles proved the same result for algebraic irrational shifts. And this dichotomy is quite common. It's usually very easy to show things about the zeta function of the Hurwitz zeta function for rational and transcendental shifts, and much harder to do the same thing for algebraic irrational shifts. And as an example, if you look in the interior of the critical strip, this result is still true. There are infinitely many zeros of the Hurwitz zeta function. This was shown by Voronin for rational shifts, Gonek for transcendental shifts, and as far as I know, this is actually not known for algebraic irrational shifts, though it's probably true for algebraic irrational shifts as well. Okay, so I'm going to switch gears for a moment and talk about moments of the zeta function. So the moments of the zeta function are sort of like a probabilistic way to look at the value distribution of zeta at the half at the critical line. So this is what's usually called the moment of zeta s. Knowing details about knowing how MKT behaves is actually quite useful in number theory, in analytic number theory. For example, if you could show that this moment is bounded above by t to the 1 plus epsilon for every k, that would imply the Lindelof hypothesis, which is an upper bound on zeta on the critical line. And if you're familiar with people working on subconvexity of L functions, you probably know that the Lindelof hypothesis is a pretty strong intermediate. It's like an intermediate goal towards proving the Riemann hypothesis. Okay, what do we know about MKT? We know quite a lot. This is actually a 100-year-old, a little more. It's a little more than 100 years old, 105 years old, I think. Old question. It was first considered by Hardy and Littlewood in 1916. They looked at the classical k equals 1 case, which is the mean square of zeta, and they showed that that's T log T. And Ingham proved the fourth moment of zeta. So, just to be sure, the way I've normalized this moment is 2k is, when k is 1, I have 2k. So the k equals 1 corresponds to the second moment, k equals 2 corresponds to the fourth moment, and so on. So the first, the second, and fourth moment are classically known, and that's pretty much all we know in terms of asymptotics. Despite 100 years of work, we actually don't know anything more about the asymptotics for any other value of k. But we do know a lot of stuff which I've put in these dots that I don't really have time to go into. But one of the things I want to highlight is that we know precise values for what ck should be. So the expectation is that this moment is T log T to the k squared, and we can actually say quite a bit about what ck should be. And the most, there's a lot of work that went into this, but the most recent thing which gave the definitive answer for what ck should be is this result of Keating and Snaith, where they used an analogy with random matrix theory to conjecture ck. Okay, so the object of this talk is the moments of the Hurwitz zeta function. So you take the definition of the moments for the zeta function on the critical line, and you replace zeta with the Hurwitz zeta function. You might expect that the shape of the moment is the same, right? So you might expect that it's T log T to the k squared, and then the constant maybe depends on alpha in some way. It probably does. What I'll try to do is, heuristically, I'll try to justify that this is actually the case for rational alpha. For irrational alpha, it's way more complicated. And if I get time in the end, I will talk a little bit about what happens there. Okay. What's known already about the Hurwitz zeta moments? So what's known is the second moment of the Hurwitz zeta function is fairly classical. You can apply the exact same methods that apply for the Riemann zeta function with no issues. And this is what Rane did in 1980. He showed that uniformly in alpha, and in particular, alpha doesn't have to be rational here. You get that this moment is T log T plus some constant that depends on T, and then this expansion in terms of alpha. And this constant is quite explicit, but I didn't want to write it down. And this error term has been improved a few times. The most recent one is due to Chan in 1993. But this is pretty much all I think that was in the literature as such. I'm now going to specialize to rational alpha and talk about what happens to the moments. Okay, so one thing is, alpha equals 1.5 is basically the zeta function. So you can assume that alpha is a rational number that is not of denominator 1 or 2. And you can assume that, it's in reduced form. So you can assume A and Q are co-prime. And the main focus is this conjecture for what the moment should be. It is the shape you would expect. And actually, the main thing in this conjecture is, what is this constant ck alpha? And I have this explicit expression for this constant that I won't really go into. All I will say is that this ck on this side is the usual constant for the moments of zeta. So you basically have the constant for zeta multiplied by some Euler product that depends on q. And the other thing I want you to notice is that ck alpha doesn't depend on A in any way. And that's actually quite straightforward to see. And hopefully we'll see it in a couple of slides. Okay. Yeah. So the thing is, the reason the rational case is easy is because it reduces to studying the Dirichlet functions. So let me quickly sketch how that happens. When alpha is A over Q and sigma is bigger than 1, this is, if you just plug in alpha equals A over Q, you get this, right? So I've just plugged in A over Q, and I've taken Q common and taken it out. Now, this thing is essentially a sum over an arithmetic progression. A plus NQ, as n varies, is a sum over an arithmetic progression. You're summing over all the m's congruent to A mod Q bigger than A. Now, A is co-prime to Q, so you probably see where the Dirichlet functions are coming in. I'm going to use orthogonality of Dirichlet characters to expand this congruence out, and you get this. And now you interchange the sums. This is a finite number of sums, and I'm in the domain of absolute convergence. So you can interchange these sums, And when you interchange these sums, you'd end up getting the inner sum will become summation m greater than equal to 1 chi m over m to the s, which is exactly the Dirichlet characters, the Dirichlet L function. And you get this equality for which holds for sigma greater than 1, and everything is analytic almost everywhere. So it follows that it must actually hold everywhere in C. Now, if you plug, what I want to do is find the 2kth moment of zeta. So I need to write down zeta s comma alpha to the k, and that's just straightforward combinatorics. You write this down using the multinomial theorem. So this k choose L is a multinomial coefficient. Here L is L is indexed by the characters mod q, this size of L equals k is the same as L1 L chi, the sum over chi L chi is equal to k. So that's just a straightforward application of the multinomial theorem. These are the multinomial coefficients, just k factorial times the product over chi L chi factorial. And then zeta s alpha is the norm squared is the same as zeta times zeta bar raised to k. So if you just plug in this expression and then bar it and multiply it with itself, you'll get two sums, 1 over L1 and 1 over L2. And then you'll get, this is the q over phi q term. You get a couple of multinomial coefficients. This s over here is the product of these chi's. It depends only on A and L1 and L2. And the L1 and L2 that I've written over here are the products over the L functions. So in other words, I'm saying L, capital Ls, this is product over chi, Ls chi raised to small l chi, right? It's exactly what you get, the exact term corresponding to bold L. Okay. And now I'm going to integrate this from t to 2t, where s is half plus it. If you do that, the expectation is if this quantity isn't a real number, it's probably going to oscillate really fast, right? And it's very easy to see when this is not a real, it's very easy to see when this doesn't oscillate. It doesn't oscillate precisely when L1 and L2 are the same tuple. So, if you also compute the sign, it's very easy to see by going back to the last slide and seeing what the expression for s is, that it's actually just 1 in this particular case. So all of that says heuristically that you can ignore the terms on integration, on integrating both sides, you can ignore the terms that are coming from anything which oscillates. And this is what you get. You get the mean square of L of this product of L functions, because these two are the same function. And then some sum over multinomial coefficients. And so the problem of looking at the moments of the Hurwitz zeta function is the same as studying the moments of products of L functions. And already you can see that this bit doesn't depend on A in any way, right? There's Q over here, there's a Q implicitly over here because the L is, L is a tuple of Dirichlet characters mod Q. But there's no dependence on A, and that's why the constant doesn't depend on A. So on the topic of moments of products of L functions, I want to highlight two previous works. One is by Heap. It says 2021, but he did it in his PhD thesis in 2014, I think. This is when it got published. He modifies this recipe of Connery, Farmer, Keating, Rubinstein, and Snaith to give a conjecture for how the moments of products of L functions should be if you're in the Selberg class and you're assuming the functions involved satisfy the orthonormality conjecture. The other work I want to highlight is Milinovich and Turnage-Butterbaugh. This is two authors, even though it looks like three. They proved that if you assume GRH for all the L functions involved, and they're automorphic L functions, not in the Selberg class, then they can show right order of magnitude bounds on upper bounds up to the small factor of log t to the epsilon. And the thing is, the class I'm looking at, which is Dirichlet L functions, trivially fall in both these classes. So their results also apply to LLS. The main theorem, the main work in the paper that I'm expositing is this theorem, which says that under some reasonable conjectures, which I won't go into, you actually can write down an asymptotic for what this should be. It depends on the it depends on Q and on the tuple L, and it grows like log T raised to the sum over chi L chi squared, right? There's a product over chi log T to the L chi squared. And I'm not going to spend too much time on what these constants are. It's probably not worth going into right now. The only thing worth talking about is like what's different from what the two things I described before, right? What's different is that Heap uses the CFKRS recipe paper. He modifies their recipe and comes up with the same conjecture. What I did instead was I used something, a technique of Gonick-Hughes and Keating known as a hybrid Euler-Hadamard product. And under some reasonable conjectures, that technique gives you the same moment, gives you the same conjecture. Right. Okay. The one thing before I pivot to talking about irrational alpha, I want to talk about how this theorem actually implies the conjecture about the Hurwitz zeta function that I had said in the beginning. The idea is you're looking at this sum, right? So you want to know which of these terms contribute the main order term, and what each of these contributed was lambda equals L chi squared, right? Each of these contribute a log T to the lambda, where lambda is this sum, where all I'm saying is in this previous slide, this guy behaves like log T to the sum chi L chi squared. So the question is, when is lambda largest, given under the constraint that the sum of L chi is K? And this is just some basic Cauchy-Schwarz. This lambda is largest precisely when all of this L, the weight is all concentrated on a single character, right? And if you plug that in, you end up getting that the one that matters most is when this product is exactly one L function raised to K. And then you just write down what this constant for this should be, and that and do some bookkeeping, and the conjecture follows from the previous theorem. There's a bunch of other stuff in that paper as evidence for this conjecture that I don't really want to go into. What I'd like to do in my remaining time is talk about what happens in the irrational alpha case. So I'm not going to do the actual moments. I'm going to look at something known as the pseudomoments. This is this quantity. So instead of looking at the Hurwitz zeta function, I'm looking at the truncated Hurwitz zeta function. So I'm truncating it at some n, looking at these moments, and then taking the limit t tends to infinity, where I've normalized this moment by 1 over t. Now, it's not obvious that this is connected to the regular moment in any way, but it actually gives you the right shape. So it won't give you the right constant, but it'll tell you what the power of log in your conjecture should be. And if you're familiar with this area, it's because of the approximate function. It's like ignoring the second half of the approximate functional equation of zeta. So if you look at this moment and you do the usual thing of taking a mean square and writing it down as something multiplied by its conjugate, this expression is precisely sum over n1 through nk and sum over m1 through mk, and then you have 1 over product over of nj plus alpha mj plus alpha to the half, and then you have this thing which is the oscillating bit, where you'll get product over m plus alpha over product over n plus alpha, the whole thing raised to it, right? Now you're integrating this from t to 2t, so this bit will actually contribute 1 only if this numerator and this denominator are equal. If they're not equal, this will oscillate very fast, and in the limit t going to infinity, it will disappear. So when you do this calculation, you end up getting that this is exactly equal to this expression that I have over here, right? And this leads you to look at this equality, n1 plus alpha up to nk plus alpha equals m1 plus alpha to mk plus alpha. If you attended Trevor's talk, you see where this is going. If you're investigating the solutions to this, you need to know something about the degree of alpha. So if alpha is transcendental, The only way this equality can happen is if this NJs and the MJs are exactly the same up to permutation. So, right, because it's otherwise it would be a algebraic relationship between involving alpha. So when you write that down, this sum just becomes essentially, MJs are given by some permutation of NJ. So it's essentially k factorial times this sum. And this sum is just log, k factorial times this, which is k factorial times log n to the k. What happens when alpha is algebraic? Well, if the degree is small enough relative to k, the exact same argument goes through, because you know that the degree is k, so it can't satisfy a relationship with degree less than k. Sorry, if you can't satisfy a relationship, with degree less than d, where d is the degree of alpha. If, on the contrary, you have k bigger than d, we now have to deal with solutions to this equation, which can arise because k is bigger than d, right? You could have that the minimal polynomial of alpha divides the algebraic relationship that this is giving. And that leads to this fairly complicated point sum. It's a logarithmic weight count, right? Because if you go back to what we're looking at, we're weighting it by 1 over nj plus alpha. So there's like a logarithmic weight, and you're counting solutions to this equality. So it gets fairly hairy, and it's not clear to me, at least, how this count behaves for large k. But you can say something if you drop the logarithmic weights, and that was the content of Trevor's talk. If you have alpha as algebraic of degree q, where k is bigger than degree d, and k is bigger than d, then this quantity, the same sum I want, but without the logarithmic weights, is actually exactly what you would get if the only solutions were the ones which involve permutations. So tk of x here is the number of ways to write m as a permutation, the m as a permutation of n. And I would not spend so much time on this because Trevor spoke about this. This leads to a conjecture, which is that if you look at the moment of the Hurwitz zeta function, it should actually be k factorial log t to the k instead of log t to the k squared. And in ongoing work, which we're in the process of writing up, Winston and I have been able to show that this conjecture is true for the fourth moment, and it's true for almost all alpha which satisfy a certain condition, which I don't really want to go into. And I think I'm at the end of my time, so thank you very much.
Thank you.